Morning guys, and welcome to this video where we're going to be building a 4-bit arithmetic and logic unit. So the components of this are simply going to be the arithmetic unit, the logic unit, and the comparator. Now the arithmetic unit is the unit where most of our calculations are performed in the computer, while the logical unit is where logic is being performed in the calculator. And the comparator simply compare the bits to see which one is greater than, if the bit is equal to or less than. So let's get started. Our aim here, we're going to have the logical operations comprising of adding 2 bits, ORing 2 bits, and noting them. And in the arithmetic operations, we're going to have the addition, the subtraction, incrementing, and decrementing operation. Now, as I said, to build an arithmetic and logic unit, we'll have to use what they call full adders. What's a full adder? A full adder simply helps us to add two numbers with binary. And now we're going to use a Y generator and a C generator. Now, the Y generator here is going to help us to what? To demonstrate the value of B, because if we're trying to build a full an ALU and we simply use just full adders or something, we'll need to build with subtractors and decrementers and incrementers, which is going to be a lot cumbersome. So we've tried to compress them into one by using a Y generator, and this Y generator simply indicates the value of B. So now, as we can see on this table simply explains us everything. Where this S0, we have the value S0, S1, Y, and C. C here is a carry out, and Y here is giving us the value of B. So C here indicates maybe which operation we're carrying. When it is 0, 0, we're going to have a normal B, and the carry out is 0. We're going to have A plus B plus 0. And now when it's normal, we're going to have A01, we're going to have A negated B plus 1. Here now, this negated B plus 1, as we did in the when we're complementing two numbers and we're adding 1, that's simply the 2's complement, and which is subtraction. Now, if we have the selection 1, 0, we're going to have the value of B as 0 and here as 1, which is simply incrementing A. And if we're having this one, it's simply going to decrement as well, sorry. So here we're having the schematics of the simple B not produced when B is produced. So let's get into Proteus and see how this works. Okay, this is our simple 4-bit arithmetic and logic unit. You see it's already running. I'll stop and start it again. Okay, now I have a 4-bit ALU. Now my 4-bit ALU is made up of B0, B1, B2, B3, A0, A1, A2, A3, and the S0 and S1. This S0 and S1 are helping us to choose which operation we want to do. If we want to actually maybe select a subtraction and incrementing or decrementing. So on the other side, we are having this S. This S helps us to choose if we want to perform an arithmetic operation or a logical operation. Now, on the other hand, we're having the output. The output is given by R, R1, R2, R3, and here the output of the comparator is given by greater than, equals to, or less than. As we see, we are having 0, 0, 0 on both bits. On A and B have 0, 0, 0. That's why you see the E. The E here stands for equals to. It turns to 1, meaning that are equal to. And so now we are at 1. We are at 1 and so we are going to move back to this table. This table is going to tell us which operation we're going to be carrying. So here the S here we have 0, 0, 0, 0, 0 and 1, 1, 1, 1, 1. So we just have two options, either 0 or a 1. And where these first four are simply the arithmetic operation, that's adding, subtraction, incrementing, and decrementing. And where S is 1, all the ones are going to be logical operations, that is and, or, and negating. So as it is set to 1 already like this, we're already in a logical region of it. We're in the logical region of it. So if now we have S1 as 0 and S0 as 0, meaning we want to perform an addition of A plus B. And if we have S1 as 0 and S0 as 1, meaning we want to perform subtraction. If we have S1 as 1 and S0 as 0, meaning we want to increment. If we have S1 as 1 and S0 as 1, meaning we want to decrement. And now if we move to the logical region, if we have 0, 0, ANDing, 0, 1, ORing, 1, 0, negating, and 1, 1, XORing. So let's try. So we simply said if this is set to 0, let's go for 0. If it is 0 means we are the arithmetic region. So if we leave it at 0, 0, we start now filling in our values. So we start from there, less significant bit. That's going to be 1 and 1, and that's 1 plus 1 I want to perform. And if I check in my answer, I have a 2. 2 is represented as 1 and 0. And if we check again in our comparator side, we see that the numbers are equal. We see that the numbers are kind of equal. That is 1 and 1. That's equal. But now, if I set something like a 3 here, and plus 1, that's going to give me a 4. And it tells me now that what? It is greater, A is greater than B. That's why it goes here to G. A is greater than B. Now, if I come here and say 3, maybe 3 plus 3, it gives me a 6 and tells me that they're equal to. And that is it. Now, let's move to the subtraction. That's A minus B, where S1 is supposed to be 0 and S0 is supposed to be 1. If we move the subtraction, S0 is supposed to be 0 and S1 is supposed to be 1, and we are still in the arithmetic region. So if we take 2 is 1, 0 minus 1. That, let me have it done back. That's going to be, if I take maybe A, 2 minus 1, that's going to give me something like, hold on a little. So instead here, subtraction is at 0 and S1 is at 0 and S0 is at 1. So if I take that and try to check my answer, that's 2 minus 1 and I have a 1. Hence it works perfectly, and it tells me again that A is greater than B, and so on and so forth. You can try it out. Now let's move by checking on the logical operations. So we're going to move S to 1 and S1 is not and see how it goes. So if I move S1 to 1, I'm in the logical section, and I move this to 0, 0, and let's say 0, 0. ANDing here has to do with like ANDing all the bits. So if I take 1 here and 1 here, you see that the 1 here occurs because ANDing only occurs when both of its bits are true. And what if I take here and here? It's normally supposed to give me a 0, right? If I take B naught, A naught, and B naught to be, if I take B naught to be 0 and A naught to be 1, it's going to give me a 0. So let's try it. That's it. It gives me a 0 and it tells me that A is greater than B. Every case it checks. Let's move to the next. It's going to be, let's move to the next, which is going to be ORing. ORing either chooses at any case. That's going to be S1 at 0 and S0 at 1. So let's move to it. S0 at 0, here at 1. So at ORing, any of them can work. That means if I fill in here, it's still going to give me 1. If I say remove this one, it's still going to give me 1. If I put this one, it's going to give 1. If I put it's going to give 1. That means if I fill any of them to 1, it's supposed to give me 1. That means it chooses any to fit, and that is it. So that is it for the demonstration on the ALU. So now we are going to now get inside of it to get the building blocks. So for the building blocks, I simply have an arithmetic unit and a logic unit. So what makes me to choose which operation I want to carry is simply the multiplexers. The multiplexer simply chooses which operation you want to have done. Let's enter into the arithmetic unit and see how it's constructed. Since I'm building a 4-bit ALU, I simply cascaded four 1-bit arithmetic units. It's simply a cascading of four 1-bit arithmetic unit 4 times. If you're constructing maybe 8-bit ALU, you're supposed to cascade it 8 times, and you're going to have 8 different outputs here. So we see that I have my cgen. My cgen simply generates me the value of my c. Now, if I get to know the structure of the cgen, if I get in here, simply an XOR gate, with S1 and S2, choosing which one to display at a given time. Now, if I move out, I enter into 1-bit arithmetic unit. The 1-bit arithmetic unit now is going to be made up of what? A full adder. Now, the full adder now here, this is simple arithmetic unit, because now this full adder now is now going to comprise of a ygen, where the ygen produces the value of b to be generated. Either b is going to be a normal b, a negated b, a 0 or a 1, depending on which operation you want to perform, if it is adding, subtracting, incrementing, or decrementing. And now my output. So let's see how the structure of the full adder looks like. It is simply a combination of these gates. Yeah, that's it. Okay, now let's get into the ygen and see how it really looks like. And that is it. Okay, I think that's it for the arithmetic unit. That means if I enter any of this, and make sure you note your numberings and your labelings over here, not to make errors. So if I get in here, I'll still have the same thing. I'll still find the same circuits everywhere. It's just a cascading. So if I enter there, I'll still see the same thing. And that is it. That's it, as simple as that. So the output is here. If I move backward, now you see that the output comes out here and it enters my multiplexers. Now multiplexers are simply, if I move in here, multiplexer actually choose the value I'm going to be selecting. This is the simple structure, and all of them have the same structure. Doesn't matter in the shape, all of them are the same. And let's move now into our logical unit. Let me move into my logical unit. Now, the logical unit is going to be made up of a logical and, logical or, logical not. Now, simplicity. If I enter into my AND, it's very simple. I'm going to simply have 4 AND gates, each having its bits of operation and each having its output. Now, if I want to produce an 8-bit logical unit, or simply add 8 of these guys again and have 8 outputs here, and that's it. Same as if I enter the OR, I will simply still have 4 of them, and if I want to produce maybe a 16 or 32 bits, I'll have 32 or 16 of them, or 8 of them. Now, if I enter the NOT, same as the NOT, I'll just have 4 of them. Maybe if I'm not in A or B, it depends on you. You can still want to add B there. You can add B there if you wish. You have to include it in your code or in your coding section of S. It's going to depend on S0 and S1, your selections. So now each of them now, which one I'm going to call is going to now pass through a multiplexer, because a multiplexer selects which operation you want to carry depending on the value of S0 and S1, as I earlier said. So as I already showed the structure of multiplexer here, there is it, here is it, here is it, and here is it. Okay, and that is it for the logical unit. Now moving to the comparator. The comparator helps us here to compare two numbers if A is greater than B, less than B, or equals to B. So as it is here, I have this set, 2-bit comparator, 2-bit comparator, which gives me a 4-bit comparator. That means it's a cascading of 2-bit comparator. And if I enter here, here is the circuit of a 2-bit comparator. Here is the circuit of the other 2-bit comparator. And now I have my 4-bit comparator here. And that gives me greater than, equals to, or less than. Good to go. And I think that's all for it. You can pause the video if you're not understanding and go over it once again to have a clear description of it. So here I have everything explained again, everything explained. So guys, if it's really complicated for you, just press the video and watch again and again to actually build it. And with this, you can build maybe a 20 bits ALU, 16 bits, 32 bits, 64 bits as you require. Thanks for watching and don't forget to subscribe for more content. So subscribe. Thank you.